Hi, in this video, we will be discussing this question together. The question is stated below. Suppose that you are given a differentiable function f whose partial derivatives up to the second order are continuous such that the second derivative fxx and a plus fyy equals 0 on the whole R2 plane. In addition, we're given the second derivative of fxx does not equal 0 on the whole R2 plane. The question is, please explain why f has no local maximum or local minimum. Before we jump into the question, let's do a quick recap on the second derivative test. I have copied the theorem here. The second derivative test shows, suppose we have a continuous function f on a disk with center AB. So here we have chosen a point AB to analyze. Suppose fx at the point AB is 0 and fy at the point AB is 0 as well. So now we're saying that the first derivative on two direction x and y are 0. So in this case, we call AB the critical point of f. So this is basically the first step we need to do in order to find a local extremum. So now we have confirmed like fx equals fy equals 0 at this point AB. The second thing you should do is you construct a determinant D where you write down fxx and fyy on the diagonal and fxy on the other diagonal. This is completely the same as stated in the theorem here. So the result should be fxx fyy minus fxx and fxy squared. So completely the same. After you calculate this value, evaluate it at AB, you will find a number, right? And the condition is A, if the number given here evaluated at AB is positive, then we take a look at fxx. If this one, fxx, is positive, then the point is a local minimum. On the other hand, if the value fxx is negative, then we call it a local maximum. In the third case, case 3, if the number you have here is negative, then it is a saddle point, and it is neither a local max nor a local minimum. All right, let's get back to the question. So now we have a special condition. The second derivative is 0. It is also shown here. So we have fxx times fyy. All right, let's do some quick calculation. Since fxx plus fyy is 0, we can move fyy to the other side. So fyy equals negative fxx. Therefore, fxx times fyy can be written into, we can replace fyy by negative fxx. So fxx times the negative fxx should be negative fxx squared. And now get back to the theorem. We have the multiple here. So the multiple here, fxx, fyy, simply equals to a negative fxx squared. So it equals negative fxx squared minus fxy squared. Now by observation, you can see something. The first term is a square with negative sign, and the second term is also a square with negative sign. That means the value here should be always negative or equal to 0. However, we have given fxx not equal to 0, and therefore the value here should be a strict negative. Let's get back to the theorem. So now, no matter which point you are at, which point you have chosen, the determinant here is always negative. So it can't be case 1 and it can't be case B as well. It can only be the third case, d smaller than 0. And therefore, there will be no local max and local minimum on the R2 plane. To be specific, we follow the following procedure. So step 1, here we do a quick review on how to find the local max and local minimum. The first step, we apply the first derivative on x and y and equate them to 0. The objective is to find the critical points. Right? After we have that, we do the second step is to find d. So d is a determinant. We write fxx, fyy on the diagonal, and fxy on the other. In this situation, we realize that the determinant is always negative, and therefore, no matter which critical points you are at, it is always a saddle point. So there are no there it's always a saddle, no maximum or minimum. And then we get back and we get to the let's look at question B. show that it is impossible for f to be constant on the unit circle x squared plus y squared equals 1. So here we quote another theorem. So EVT, extreme value theorem. So EVT states consider a closed interval with a continuous function f, and then f has its absolute maximum and minimum within the domain. Within that interval. So it is like, suppose we have a closed region, and then if your function f is continuous over this region, then there has to be an absolute maximum and minimum inside this interval. So let's get back to the problem. This question states, let's consider an interval x squared plus y squared smaller than 1. So it is a unit circle, right? And since f is continuous over this region, there has to be an absolute maximum and minimum within this region. Okay, so let's consider the unit circle. And we also have f is continuous over this circle. Therefore, by extreme value theorem, what do we have? We know f has its local, f has its absolute maximum and minimum within the region. Okay, so now let's find the absolute maximum and minimum inside this region. The first thing is to find the local max and local min, and we compare them to find the absolute ones. However, from question A, we realize that we will not have any local maximum or minimum within this range because the condition here is very strict. So there will be no local extremum inside a region. As a result, the local extremum should appear on the boundary of this region. That means x squared plus y squared equals 1. So there are no there is no chance that local max and local mean are inside the circle. It should be at the boundary. Or they should be on the boundary. The boundary, what is the boundary of the unit circle? X squared plus y squared equals 1. Next, we realize the second condition, another condition. So we suppose f of x, y is constant on the unit circle. So we wish to show it impossible. So we do it conversely. We prove by contradiction here. So let's suppose f of xy is constant on the unit circle. Now we prove it by contradiction. So we suppose f of xy is constant c, so let's call it c, on the unit circle, x squared plus y squared equals 1. All right, we suppose that f is a constant on the unit circle. And again, by EVT, f has its local max and minimum on the boundary, right? Because there is no chance that an absolute extremum within the region. So it should be on the boundary. However, on the boundary, f of xy is simply a constant. That means the absolute the local max, the absolute max equals absolute minimum equals the constant c, right? The absolute value should and can only be on the boundary, but the boundary is always a constant. So absolute max equals absolute mean equals the constant c. All right. Now we have shown the absolute max and absolute mean of the function c is c. So the highest value and the lowest value of f should be c. That means f of xy equals a constant c on the whole circle. Oh, circle plus y squared is smaller than 1. Because c is the only value that can appear in the range. However, this contradicts to the assumption, because if f is a constant over the region, the second derivative can only be 0. So the assumption fxx not equals 0 cannot be true. Fxx equals 0, and this is the contradiction. The problem is that the boundary of f cannot be a constant. So it is impossible for f to be constant on the unit circle. All right, that's it.